Namaskar, good evening everyone, and welcome to today's NAST webinar. National Anveshika Network of India NANI, a proud initiative of Indian Association of Physics Teachers IAPT and Shiksha Sopan. This is Vimal Kumar. Today we have honor of hosting Dr. Prabhat Verma, a renowned professor of applied physics at Osaka University, Japan. As we gather here on this special day, May 11, 2024 at 6 p.m. IST. Our focus is on exploring the fascinating world of light at the nanoscale, a topic that holds immense potential for revolutionizing our understanding and application of photonics. Dr. Prabhat Verma is a distinguished professor of physics at Osaka University in Japan, where he leads a research team on nanospectroscopy and nanophotonics. He is a fellow of Optica, formerly OSA, SPIE, and JSAP, Japan Society of Applied Physics, with a master's degree from IIT Kanpur and PhD from IIT Delhi, followed by postdoctoral research in Germany and Japan. Dr. Verma brings a wealth of expertise to his field. His extensive publications record numerous international conference presentations and editorial roles in esteemed journals underscore his standing as a leading authority in applied physics. Dr. Verma's expertise in the field of applied physics, particularly his groundbreaking research on photonics, makes him an ideal guide for today's webinar. His work dwells into the intricate dance of photons, the smallest discrete unit of light, and how they interact at the nanoscale. This exploration is not just about the beauty of science, but also about the practical application that could transform our lives from energy efficiency to healthcare and beyond. As we embark on this journey with Dr. Verma, we aim to shed light on the complexity of photonics, demystifying concepts that often seem abstract. We will dwell into how photons behave differently at the nanoscale, influencing everything from the efficiency of solar cells to the speed of internet communication. Through his insights, we hope to inspire a new generation of scientists and enthusiasts who are curious about the world around them and eager to contribute to the advancement of knowledge. This webinar is not just an opportunity to learn, it is a chance to engage with one of the leading minds in the applied physics. We invite you to ask questions, share your thoughts, and join us in exploring the light at the nanoscale. As we already know, we have 45 minutes of the presentation and 25 minutes for the Q&A session. I kindly request that everyone keep your questions with you during the presentation session, and you will get a chance to ask your question in the Q&A session. Together, let's illuminate the path towards a deeper understanding of photonics and its impact on our life. Thank you for joining us today. Let's dive into the fascinating world of light at the nanoscale, guided by the expertise of Dr. Prabhat Verma. Welcome, sir.
Thank you so much, Vimal. I'm a little bit surprised to see how much you have spoken about me. I don't know if I can really do everything that you have said, but thank you very much. I think I was not sure whether I have to speak in English or Hindi, but I'm going to speak in English. And if you have any question, you can please feel free to ask me even in Hindi. Don't worry about it. Okay, so let me share my slide. I hope you can see my slides. Is this working for everybody?
Yes, sir.
Okay, thank you very much. All right. So the title of my talk is Light at the Nanoscale, from Photon to Photonics. Maybe I will be giving you a few kind of new concept, at least for some of them, some of you. So please feel free to ask questions if you have anything in your mind. And we are actually very close to International Light Day. So I would like to congratulate you a few days before this day, because actually every day is Day of Light for us. And especially I'm here in Osaka city in Japan, and Osaka is known for City of Light. You can see this is a picture from the downtown where everything is so much illuminated. And you can see many of such situations there. So I'm really in the perfect place where I'm studying about or doing research about light, related to light. Light is very important for our life, as you can understand, that without light, we don't even have our life. Food is essentially from light. And then we have so many other things where light is used. And even for cooking, here you can see a demonstration where a pressure cooker is kept on a kind of lens, a mirror, I would say, which focuses sunlight to this pressure cooker. And they are demonstrating very nice cooking here. Of course, light has been always there with mankind, starting from Stone Age, where I think they started using light for lightning, uh, starting from creating flames or fire from stones. And then we went slowly and slowly up to today's time, where we have LEDs as lightning. Uh, More than lightning, basically, we have been using light for many different purposes. So I would like to comment a bit on evolution of light and the technology and applications related to light. Basically, light that we see today, or as we understand today, uh, it is started from Maxwell's time, when he says that this is, or he somehow confirmed that it is electromagnetic wave. And then the contribution from J.J. Thomson and Leonard and Einstein in 1905 was to somehow come to a conclusion that light is also a particle, which is photons. So this era, I would say, that where people were trying to understand what light is, whether it is particle or it is wave or it is both. And then after they developed this understanding, there were lots of applications of the technology. And Einstein in 1917, he discussed about stimulated emission, which basically led to the innovation of lasers. So we started innovations from maybe 1960, quite late after that, but it was inspired by Einstein's research. And then slowly and slowly we are going ahead. LED, first it was red, then yellow, green, and then finally blue very recently, which allowed us to have combination of these colors to make some kind of white light. Then fibers, integrated photonics, semiconductor photonics, and waveguides, and then finally application of these fiber optics in communications. So this era is basically the photonics era, when light was used for technology and application. So basically, you can just say photonics is the science and technology of generating or controlling or detecting photons, or even making new applications of that. So I'm listing here some of very interesting and important things that have been there in the past. One of the most important one is optical communication. Somebody is, I think, writing, so please stop writing on this. Healthcare has been very important field where light has been used. Then consumer electronics, as you know, you have, for example, mobile phone in your hand. The screen of that is one example of consumer electronics where light is used. Then solar cells, they are very prominently used. Various kind of light sensors, starting from very short wavelength to long wavelength, not only in the visible range. Then quantum computing is coming up, then autonomous vehicles, LiDAR and AR, VR, everything. There are so many things which are related to photonics that we can see in today's time. But let us first understand what light actually is. We can say it is photon, it is particle, and it is also wave. And when it is wave, when it is particle, well, it is decided by light when it behaves like wave, when it behaves like particle, but basically it is both, because even when we call it a particle, photon, we associate it with energy, momentum, and also wavelength, which comes from the wave nature of light. So let's consider it as a wave. So electromagnetic wave, where electron, electric field, and magnetic field, they oscillate perpendicular to each other like this. Now, where is this electric and magnetic field coming? Because the light can travel for very, very long distance where there is nothing from the vacuum, for example. So we all know that light, electric field can be created by electric charges, or magnetic field can be created by magnets, but we don't have any of them. So what are the other origins for creating electric field or magnetic field? Of course, the variation, time variation of electric field can create magnetic field, and similarly, time variation of magnetic field can create electric field. So we have been through this kind of experiments in our childhood, where you can see that changing magnetic field can create electric field, and changing electric field can create magnetic field. If the change in the field is constant, that means if, for example, in the left side, magnetic field increases constantly, then there will be a constant electric field generated, and vice versa in the case of electric field when it changes constantly. But if electric field doesn't change constantly, but it changes with some variation, then magnetic field created will not be constant. Or similarly, if the magnetic field doesn't change constantly, then electric field will not be constant. So in this case, what happens is that electric field is oscillating, and then that creates oscillating magnetic field. And then oscillating magnetic field creates electric field. So they basically create each other, right? So E creates B, and in turns B creates E, and then again E creates B, and so on. So the energy is transferred between them. So E and B, that means electric and magnetic field, are basically interlinked. They create each other. So this is very interesting situation where we have electric and magnetic field by themselves, and they are together, and they are so interlinked that you cannot have one without other. Right. So if we look at the visible range of light, you can see that we often display like this colorful display. So how many colors are there in this visible light? Nowadays, when we have LED lights, we say that, okay, 3 colors are enough. They can make any color. So can we say there are 3 colors? In some culture, they say 6 colors. In some cultures, including Indian culture, they say 7 colors. But also you can see the color is continuous. So maybe infinite colors. So the question is, how many colors are here? It is made by electric and magnetic field, right? So does electric field have any color? No, it doesn't. Does magnetic field have any color? That doesn't. So light is basically a combination of these two fields. They are together. So how come they create color when they individually don't have color? So the question is, does color even exist? Let me give you one example. Let's say you have a yellow light, 550 nanometer wavelength, and you have red light, which is 650 nanometer wavelength. Now, if you shine these two lights at one white place, you can see a kind of orange color, which is combination of yellow and red. But orange color has a wavelength of about 600 nanometer. Does it mean that we have 600 nanometer wavelength there? No, because we have only two wavelengths, 550 and 650. So the color is something very different than the wavelength, right? So that means the question is there, what is the color in this case? Look at light when it passes through any medium, for example, glass. Let's say it has a refractive index n, then here the speed of light will decrease when it goes inside, and similarly, the wavelength will also reduce. So that means the wavelength is different when light enters this glass, right? So does the color of light change inside the glass? This is very simple to do experiment, and we can see here. So the light doesn't seem to change its color when it passes through the glass, right? So it appears to have exactly the same color. So then it is a bit confusing what is happening here. Let's see how exactly we see something. So it looks like it doesn't really depend on lambda. How do we see? Obviously, we see with eyes, with the aid of light. What is inside our eye? One is optical component here, which is lens, and then we have optical sensors. So this lens will focus whatever you are seeing to this sensor. That means the light falls ultimately on the sensors. These sensors convert this light into electric signal, and that electric signal goes via optical nerves to our brain. So our eyes receive light, and then it converts into electric signal. That electric signal goes to our brain, and then finally we say that we see something. And what kind of light we can see, it really depends on the sensor, because the sensor can sense certain kind of light and it doesn't sense other light. So that is why we have so-called visible light, which is approximately about 400 to 750 nanometers. So only these wavelengths can be sensed by the sensor that we have. Of course, some animals have different kind of sensors, so they can see in the night. That means they can see infrared light or other wavelengths, so they can still see, but we don't. This is the visible light. And so the point is that, do we all see the same color? Because this is seen by the brain, and the brain is a biological thing which is different for different people. So the question is, my red is same as your red, or my blue is same as your blue? So what is the color of any object anyway? Actually, the object or even the light, I can say that it doesn't really have a color. Color is something that we perceive in our brain, because brain doesn't receive any light. Brain receives only electric signal, something that we feel, experience, and then finally ultimately recognize it. So it is a combined effort of our eyes and brains that interprets light as a color. So for example, if we have an object here, this object is making the image, then it converts into signal and goes to the brain. So our brain is trained to see that particular electric signal as this particular color. And that can be different for different people, because this is two people are not the same. So they are biological things inside their brain. How the light is converted into electric signal, how it is sent to the brain, and how brain recognizes it is really different. So it may differ from person to person. Different people can see it in a different way. Basically, we see light when it is going into our eye, right? So what happened in the case of glass that we see earlier? Light has to go into our eye. So that means when light is inside glass, we don't really see that light because it's not going into our eyes. Or even light outside glass is not going into eyes, and we are not going to see that. So only when this light is scatters, maybe we have some dust particles, maybe we have something that scatters the light, and then scattered lights go into our eye, then we can see that. So as soon as it comes out of the glass, again its wavelength becomes the same, and then ultimately it goes into the eye, and eye also has some kind of fluid, so it has a different refractive index. And so the wavelength again changes inside eye. And then that is the wavelength that goes to the sensor, right? So what our eye see is the wavelength inside our eye. And of course, that will depend for that will be different for different people, because the fluid inside eye of two people may not be the same, right? So let's say if I have an object and we shine multiple wavelengths, then this particular thing, which I would say does not have any color, it only scatters one particular wavelength. It doesn't scatter other wavelength. That's the only thing. It is the characteristic of this light, this object. So this object does not have a color, but it has a property that it scatters, let's say 660 nanometer. Then that goes into our eye, and then the wavelength changes again inside our eye, and then the brain sees that signal corresponding to this wavelength, and it thinks, it is trained to think that this is the red color. And so that's how we perceive the color. Okay, so the question still remains, what is the color of an object or light? So wavelength depends on the medium in which it travels, and ultimately it goes to eyes. So it depends on the eyes that sees it, right? So that means what sensor sense in our eyes is not really the wavelength, but it is the energy that we are seeing, because the light goes inside our eye, and ultimately the light vanishes. All its energy goes to the sensor. It is converted to electric signals, and then it goes to the brain. So it's the energy, and energy is always constant unless there is some loss. So the energy can be written like this for light, where H is constant. So that means the frequency always remains constant, because E is constant, right? But lambda can change because velocity is changing. I mean, speed is changing. So C changes, so lambda changes, because E remains constant. So it is the frequency or the energy which remains the same, which does not change. It does not depend on I, it does not depend on medium or anything. So if we want to consider something related to color, it should be associated to frequency or energy, not to the wavelength. So first of all, let's understand that anything, any object does not have a color of itself. It just scatters certain wavelength or certain energy. And that energy is sensed by us. So we can rather associate it with frequency and energy, because color is something that we have always been talking about. So we assume that color exists, but then it should be associated to frequency or energy rather than the wavelength. And this is an important message here, because now what I'm going to do, what I'm going to talk about is about nanoscale, light at nanoscale. And that place, wavelength is going to change, but the energy will not. That means the frequency will not change, and that is how we are going to consider light. All right. So when we talk about nano world, what happens to light in nano world? Light frequency, wavelength of light is already in terms of nanometers, but not really nanometers, several hundreds of nanometer, right? So if we consider, for example, visible light, let's say lambda is about 500 nanometer, then we are talking about nanomaterial or nanoparticle, let's say something like 10 nanometer. So this is quite small, maybe 50 times smaller than the wavelength of light. So when light passes through it, the electric field remains almost constant everywhere, this particle. Of course, as light passes, its electric field is oscillating. Somewhere it is going up, somewhere it is going down. But within the particle, it is so small that electric field is always same. So it doesn't recognize the light. It doesn't recognize any variation in electric field or magnetic field, and so it does not recognize the light at all. So this is what happens, that when we have light with very large wavelength and our object is very small, then the visible light does not at all interact with a small nanoparticle. So the things are slightly different at nanoscale. For example, when we consider about making image of and sample using a lens, we always studied something like this, which we call as ray diagram. So we have a sample as a point sample, and then we have an image which is as a point image. But this doesn't really work perfectly at nanoscale, because the electric field, variation in electric field is much larger than nanoscale. And so that's why we cannot really consider something like this. What we have to consider is that the light focuses in a spot, not in a kind of point. So even our sample is too small, maybe not really point object, but still very small nano size object, then the image will be much larger, something like this. And this image will be in the direction of light, maybe about few micrometers. And in this direction, it's going to depend on lambda, and it is lambda by 2, which I'm going to discuss very soon. So that means for visible light, lambda by 2 is about 200 to 350 nanometer. So the focus spot here, or the image size of the image, is going to be this much, even though our sample is just few nanometer, let's say 5 nanometer or 10 nanometer, the image will still be 200 or 300 nanometer. And so we lose, what we lose information about the shape, because if there is a variation in the shape at nanoscale, we don't see that. And also we lose the information about the size. And everything which is very small will always appear like a big image here, right? So the cross section of this, if I look at cross section, the cross section will be something like a circle. Okay, so let's consider this. Let's say we have two particles here. One is here, one is here. They are separated by a distance d. And so the image will be something like this, because both of them will show a larger image. If the distance is large enough, we can say that, okay, there are two particles very clearly seen, so we can call them fully resolved. So if this is the distance, then they are actually fully resolved. And if we reduce the distance a bit, then they start to overlap. We can still understand that there are two objects, but they overlap. But in this case, if they are too close to each other, they completely almost overlap, even though the particles you can see here, they are separate by few nanometer, but the image is not resolved. So this situation where we can barely see is called diffraction limited situation. And in this case, d is lambda by 2n sine theta. N is the refractive index of this lens, and sine theta depends on the size of the lens, because theta is the direction at which maximum direction at which light can go. So if the lens is small, then theta will be small. Lens is large, then it will be large. But there are some limitations on theta and n, and basically it is almost equal to 1 for natural materials. So that means this comes out to be lambda by 2. And this was understood or clarified by this guy called Ernst Abbe. He was a scientist in Germany. And that is why this is called Abbe's diffraction limit. So we have an Abbe's diffraction limit that says that the light two objects cannot be separately seen if they are if the distance between them is smaller than lambda by 2. And so the same thing happened for single particle also. If the particle is very small, then the minimum size that you can see is lambda by 2. And lambda by 2 is too large if we are talking about nanoparticles. So we need to do something about it. Right. So the question is, why do we have this diffraction limit? Of course, there are some calculations that you can do. Why it is called diffraction limit is because it depends on the diffraction of light, and it can be calculated. But we can also understand somehow why it happens, because the light actually has two components. One is propagating component, one is non-propagating component. So many of you probably will hear it for the first time, but light always have propagating and non-propagating component, and non-propagating component is called evanescent light. Propagating means it travels for a long distance. For example, light coming from sun or stars. So that means their amplitude remains exactly the same like this, so that they can propagate for a very long distance. But if by chance the amplitude decreases slowly and slowly, then finally, after a certain distance, it will become zero intensity. So that light will not propagate anymore. That's why it is called non-propagating light. And this light is always there. So if we take any source, from that source, we have a propagating light and we have non-propagating light. That means evanescent light. Now, of course, this evanescent light cannot go to our eyes because it vanishes very quickly within few tenths of nanometer. It vanishes within few tenths of nanometer. So what we see is always propagating light. We never ever see this evanescent light, but this always exists. And not only from the source, which is you can call primary source, but also secondary source. For example, from a lens. So if you shine light on the lens, the other side, you will have again both propagating and non-propagating light. Or if you have a kind of small particle, which is scattering point, if light is scatters by this, again, we have propagating and non-propagating light. So now the thing is that because of this reason, the non-propagating light is lost, and non-propagating light also has some information, so that information is lost. So for example, if you want to make image using a lens, then let's say this light is coming from the object, and then it goes to the lens, and then after lens, only the propagating component goes to make the image, and this component, which is non-propagating, is lost. And all this information is coming from the object. That means the information content in this part of light is lost. And so we lose something in the image. What do we lose? We lose the information about size and shape, as I explained to you before. And that is the reason why we lose this information, is because the evanescent light is not participating in the image. So that means if we want to make image of nano-size particles or nano-size materials using light, then we must involve evanescent light because it has that information. So if we involve this evanescent light into that imaging process, only then we can make the image with nano size. Okay.
Excuse me, sir.
Yes.
Sir,
Yes. Go ahead.
you're saying that we will lose the information in the process,
Yes.
but quantum theory suggests that we can that information cannot be destroyed.
Okay, so let me finish my talk and then you can ask me later questions, okay? So that we can continue in the flow, and you can keep your questions for time being, and we can discuss this after I finish the talk, okay? All right, so the diffraction limit of light, as I already discussed, is about this size, lambda by 2. And now we want to break this limit because we want to go beyond that so that we can measure something which is at nanoscale. So this also means, if we still think about this, this also means that if we reduce lambda to a very small value somehow, then this will also be lambda by 2 will also be the very small. But we don't want to go to X-ray. We want to keep the same energy because we have to use visible light for many things. And we want to keep the same frequency or same energy as visible light, but we want to reduce lambda to very, very small value, maybe a few nanometer or so. So this is done by using some kind of metallic nanoparticles. And the question is, why do we use metal? Actually, I will not go into too much of details, but I will give you some idea. So why not something else like insulator or semiconductor? Is because it has freely moving electrons. Electrons are free to move around in a metal, right? Because you know that electron can pass through metal, you can have current in metal. If you touch electricity by metallic thing, you will get a shock. But if it is insulator, nothing happens. So what's the difference between them? The classical picture is very simple. The classical picture is something like this. if inside the material, if you consider that atoms are separated, if the atoms are separated from each other, then the electron which are attached to one atom can never move to other atom. And so it will remain confined to this atom, and this electron will remain confined to this atom. That means the electrons do not move around in an insulator. But again, in the classical picture, the metal can be considered something like this, where let's say the electron orbits overlap with each other. So the electron can move from one atom to other, and other. So the electron is always attached to one of the atoms, but still it is free to move around in the metal because it can move from one atom to another atom. And of course, when an electron moves, maybe it leaves behind an atom minus one electron. That means it leaves behind positive charge. So that means in the metal, we have lots of free charge carriers, right? Positive charges and negative charges. Here, positive charge does not mean proton. Here, positive charge means atom minus electron. So we have positive and negative charges, and they are free to move around. So these free charge carriers actually are called plasmons. So plasmons are nothing but free charge carriers. And so this kind of study is also called plasmonics because it is related to plasmons. But don't worry, plasmons was just a simple thing. It's just free charge carriers which are there in metal. Anyway, so we are not interested in bigger material, bigger metal, but we are interested in nano metal. So let's say if we have a nanometal here, so if we have a metal nanoparticle, nano means it is much, much smaller than the wavelength of light, and we shine light on this, then what happens? Now, when light passes through this material, and let's say this electric field E represents here the electric field at the moment around here, of course, this electric field is going to change, it's going to oscillate. Then let's zoom this particle and see it in a bigger picture. So this is our nanoparticle, and this electric field is coming from the light that we shine on it. This light is a propagating light, so normal light with a large lambda, okay? Now, because of this electric field, since this is metal, it has free charge carriers, positive charges and negative charges, and they are free to move, and there is an electric field, so they will move, right? So they will move like this. Electric field will move positive charge in this direction, and the negative charges will go in the opposite direction. So because of this redistribution of charge, there will be a new electric field created around the surface like this by this charge. And this electric field is going to oscillate because this light is oscillating, right? You can see on the left side. So the propagating light that falls on it, electric field is oscillating. So that means the positive and negative charges, they will go up and down, and they will oscillate in the nanoparticle. That means the electric field created by this is going to oscillate. So this electric field, if I look at certain point, for example, let's see, I look at this point. So this electric field will oscillate exactly same as this electric field, exactly same as this electric field, right? And so this oscillating electric field is going to create a magnetic field, and that magnetic field is also going to oscillate. With what frequency? Exactly same frequency as the propagating light, because the propagating light is forcing it to oscillate exactly at the same frequency, right? And what happens if we go away from the surface? If we go away from the surface, we are going away from the charge. So that means the electric field will reduce. So electric field will become weaker, and the magnetic field will also become weaker. So here we have a strong electric field which creates a strong magnetic field. They oscillate. So we have a strong oscillating electromagnetic field. But when we go slightly away, their intensity will decrease, amplitude will decrease. As we go away, it will also decrease. So we have oscillating electromagnetic field. That means we have light here. This light is in addition to the propagating light. And this light is decreasing in intensity as we are going away. So this light is something like this, where its intensity is changing. And this is, I'm just showing in one direction. This happens in every direction, right? So that means we have a kind of light which is not propagating, non-propagating light. So this is evanescent light, and this is confined near this particle because it's not going away from the particle. When we go away, the electric field becomes zero. So ultimately, the situation will be something like this. So you shine light on a particle and you create evanescent light around it, and within few tens of nanometer, it's going to become almost zero, right? So that means by doing this, we can create evanescent light and then use that evanescent light for making any kind of optical measurement. And then, for example, imaging, we can make images, we can make any other kind of optical measurement, and that will be with evanescent light. So if we put a sample around here, then we can make image with that kind of situation. And so we will get very high resolution. And this is also enhanced because the energy is coming from the propagating light. Propagating light is the reason why they oscillate. So the energy is transferred or dumped from the propagating light to this oscillating electromagnetic field. That means to this enhanced and confined evanescent light. So this light is very interesting, which is created around here. All right. So now let's see what happens to the wavelength and to the energy of the light. So we understand that this light, which is created here, has a wavelength which is decreasing, sorry, the amplitude which is decreasing slowly and slowly. So decreasing amplitude ultimately becomes zero, so the intensity of the light becomes zero. And this oscillation is because of the charge which is distributed only within few nanometer. So the wavelength, if we say so, if we consider wavelength associated to this evanescent light, that wavelength is also going to be of the same size as the particle. So it is going to be of nanometer size. But the frequency, as we saw, is actually same as the frequency of the oscillating electromagnetic field of the propagating light, because this oscillation is forced by the oscillation of this light. So the wavelength of this evanescent light is extremely small, but the frequency is exactly same. And so, as I said before, we should associate color to the frequency, not to the wavelength. So that means the color of the light is exactly same as the propagating light. So if we shine green light, we get green evanescent light. That means green light which is not moving, green light which is confined within few nanometer. So this kind of light is actually very interesting because it has same frequency, so it has same energy, so it's going to do everything. If you use it in any experiment, it's going to do everything as the propagating light would do, but it is non-propagating and it is confined, and its wavelength is extremely small. But one of the question is that if it is not moving, then what is happening to the energy? So can we see this color? Because I said that it has color, but can we see? Of course, we cannot see because it is non-propagating. It doesn't go into our eyes. But at the same time, let's say if I shine light on a particle and I create evanescent light, then where is the energy going? I am dumping energy from this light, but that energy is not going away because this evanescent light does not move. So that means the energy is confined around the nanoparticle. So if I keep on shining light, the energy will build up, but the particle cannot continuously receive energy if it has to be stable. Otherwise, what will happen is temperature will increase, it will melt and burn, and everything will be gone away. So what is happening here? If we shine light, what happens to that energy? Actually, for stability, it is necessary that if something receives energy, it has to give away exactly same energy so that no change in energy. For example, if we consider our Earth and Sun system, then the sun continuously shines light on Earth from every side, day and night, right? So Earth is continuously receiving some energy. Why does Earth's temperature not increase every moment? Because even if it increases by a fraction of degree, in hundreds of years, it will burn away, right? It will so high that we cannot live there, cannot imagine there. So basically, it also radiates. So it receives light and it radiates light. So it receives energy and it radiates energy, so that the incoming energy and outgoing energy is exactly the same. If there is even very small difference, then after a couple of hundreds or thousand years, it's going to burn, right? So that means it has to be incoming energy must be exactly same as outgoing energy. So here also the same thing should happen. That means it must radiate. How much? Exactly same as what it receives. So if I look at for example, this is the frequency and intensity. So at certain frequency, let's say high intensity, another frequency you don't have. So if this is the light that is shine on it, this is the energy it receives, then it must scatter exactly same energy. So it creates evanescent light as much as it can, and then it has to radiate exactly same. So the incoming energy must be exactly same as the scattered energy. So that means the shape and the frequency, everything should be exactly the same. So you can say that in this case, the propagating light that shines on this creates the evanescent light. It builds up energy there, and then it is scattered. So that means then in the next step, the evanescent light is converted into the propagating light. Okay, so somebody is keep writing on this board, so please stop writing. Okay, so propagating light is converted into evanescent in one step, and in the second step, the evanescent light is converted into propagating light. And as I said, they are exactly the same. They have to be exactly the same in energy and all. So we cannot see this light because this is non-propagating, but this energy which is scattered is exactly the same. So evanescent and scattered light have identical properties, and this is scattered light is propagating light. So that means we can see that. So by looking at this scattered light, which is identical with the evanescent light, we can understand everything about evanescent light. What is the color, what is the frequency, what is the energy, how it behaves, and so on, right? So from propagating light, we convert evanescent, and from evanescent, it converts into propagating. So we, or maybe if you use some machine to do measurements, like a spectrometer or something. So we or a machine cannot see the evanescent light, but we can see the properties of the evanescent light through the scattered light because it is exactly the same, right? So also, I was showing you this kind of curve without going into the detail. Actually, the frequency also depends also on the size and the metal and so on. But again, I will not go into the detail, which is somehow you can understand it's the resonance phenomena. So every small particle will have certain resonance. So without going into the detail, I just say that if you illuminate white light, this will preferably create evanescent light around one particular frequency. And so this evanescent light and so the scattered light will have a certain behavior depending upon what kind of metal it is and what is the size. And I just want to give you an example. Here are different nanomaterials, nanoparticles of silver, and they are put into the water and shine light on that, and they show such a beautiful color. So you may think that this is kind of luminescence, but it is not. It is just the scattering of light. And since they have different kind of size, or maybe different, in this case, they are all silver, but this could be different particle, different metal also. So they have different kind of a scattered light, and that is why we have this kind of light. And this field of science, which is called plasmonics because it uses plasmons, is very recent. But several hundred years ago, people already understood this phenomena without knowing what is happening. So they saw that the particle, when the particle size is different, it scatters different kind of light. And so this was used especially in France and in Europe in many places. This is a very famous church in Paris called Notre Dame. And you can see these windows around here. They are made by that kind of, they are made of glass, and those glass have some nanoparticles of metals. And then when light shines, it looks something like this, such a beautiful. So these colors are not paints. These colors don't have any pigments. They are just nanoparticles. And there are many examples of this kind of pictures around Europe. You can see they have made such a beautiful things without even knowing what is happening here, without knowing what is plasmonics, but they did it. Well, anyway, so using this kind of evanescent light, we can make many kind of nano optical measurements. And especially in my research, I am working on making images. So what we do is that we put these nanoparticles on the sample and actually control those nanoparticles, so we can move around that nanoparticle on the sample and shine light. So when we shine light around the nanoparticle, evanescent light is created and then move around that particle to make images. So I would like to show you some examples. Here, this is optical nanoimaging through confined evanescent light. So this kind of particle we put on the sample and then move around. So there is a special technique for that. I'm not going into the detail. Here is an image of carbon nanotube. Actually, all of them are carbon nanotubes. And you can see that carbon nanotube has a size of about 2 nanometer or less than 2 nanometer. So, and this particle was about 10 nanometers, so we can get a special resolution of same size as the particle. So we can see only 10 nanometer resolution size, right? This is just impossible by visible light, because visible light always confines to lambda by 2. And here we are using 530 nanometer. So that means around 250 or even more than that is the limit. In this case, the resolution is 8 nanometer. Here is again 10 nanometer. And this is very interesting. This was actually one single carbon nanotube, straight carbon nanotube. And we pushed this carbon nanotube by some kind of small tip. And by pushing, we made this kind of pushing in different direction. We pushed in this direction, then this direction, this direction, this direction. Ultimately, we made something like C, N, and T. So it's CNT made of CNT. And during this process, the carbon nanotube rolls and is stretched. So it develops lots of strain and stress and strain inside. And this image shows the distribution of strain and stress at nanoscale within one single carbon nanotube. So this is very interesting result. So these kind of things can be done. And then there are many other materials. This is graphene, and different colors here show different number of layers. This is also similar material called MOS2, which also has different number. These are layered two-dimensional samples. So they have different number of layers. They are shown in different colors. And here is some acting filaments in cell, and they are all at nanoscale. So this kind of very interesting research can be done. There are many others. So I just listed some results from my own group. But there are so many things, and I call this era as an era of nanophotonics. So compared to photonics, there are so many other things, interesting things that we can do. Of course, we can do super resolution microscopy. Some examples I have given you. Then we can do nano optical investigation, because now light is confined within nano size. So you can investigate many things. For example, these days, now the transistors are made at 5 nanometer or even 3 nanometer size, right? So new iPhones are made with transistors of 3 nanometer size. There is no way to see what is happening at 3 nanometer within that transistor. But this kind of optical technique can probably tell you many things about how those semiconductors are inside that transistor and so on. Then plasmonic sensors, they are very interesting. They have been used for detecting many kind of things, especially viruses. So for example, for COVID-19, it was very useful to sense by plasmonic sensors, which is done within few seconds, doesn't take any time. And it is very frequently used for pregnancy test and many other kind of biological tests. Nano lasers can be made with this, then plasmon enhanced solar cells, biomolecules like proteins which are of nano size can be visualized, nano-optical cancer therapy, then food safety and metamaterials, many things. And uh, just to again list few of them, this plasmonics, that means the technique that I have just shown you, it used for self-driving cars because it uses LiDAR and so on. Then this is cloaking like Mr. India, that means one can disappear, invisible. That is done by metamaterials, which is also based on plasmonics. Then we have, of course, much better optical computers, super fast computers, high resolution devices, solar cells, and many other things. And I am very much interested in particularly two things other than imaging. So I will just give you example of two things out of these. One is cancer therapy. So, cancer is a cell that grows very fast. So because of this property, it is very easy to use this property for nano-optical treatment. Since it grows very fast, so it needs lots of blood, lots of oxygen. So when cancer cells are grown, they create new blood vessels, very thin blood vessels around them so that they can receive blood supply and for oxygen also. Oxygen, of course, comes with blood. So whenever there is a kind of cancerous tumor, around tumor there will be lots of blood cells, blood vessels, which is created by them. So what one can do is inject some plasmonic nanoparticle, that means metallic nanoparticle, in the blood. Then, of course, it goes everywhere in the body. But since cancer cell needs much more blood than anything else, so much more blood flows to the cancer cell, and so much more these nanoparticles go into the nanocell. So what happens is that you can selectively include or selectively collect nanoparticles in the cancer cells. And then you shine light from the top. So of course, if you are shining light from on the body from the top, then visible light does not have that penetration, but NRI light, near IR light, can penetrate through our body. So that means if we, without any operation, we shine light, then the light falls on these nanoparticles and enhanced evanescent light is created. And if you control the energy of this near infrared light, then you can create very strong near field light, very strong evanescent light. It's so strong that it will kill these cancer cells. So finally, the cancer cells can die. So selectively killing the cancer cell. Why selectively? Because these nanoparticles selectively collect in large density only where there are too much of blood. So that's why you can target like surgical killing. So you can target these cancer cells and kill them using light. So this is very interesting upcoming technology for cancer treatment. And similarly for solar cells. So similarly, you create nanoparticles inside, and then when sunlight falls on them, these are nanoparticles inside solar cell material. When sunlight falls, then they create very strong evanescent light. And if there are too many particles, they collectively enhance the response of the solar cell, and the solar cell actually behaves in a much better way with very high efficiency. So these are just examples, but there are many other applications of nanophotonics. So I think I will stop here And I will just like to mention that this field received a Nobel Prize in 2014. Actually, it was not on exactly the same technique that I have explained, but it was also super resolution optical technique. And the three guys who received this Nobel Prize were Eric Betzit, Stephen Hell, and William Morner. And this guy, I had the opportunity to meet him maybe just few months before he got Nobel Prize. So this is an old picture here. So anyway, thank you very much for today. And now if you have any question, I will be happy to answer them. Thank you.
Good evening, sir.
Yes.
I am Chandrabhanu Gupta from Bihar, and I am asking you when
Yes.
light enters from air to glass, then wavelength decreases to 4 to 5 nanometer, and this is the wavelength of just like a blue color, I think so much. And then light enters from air to glass, then why color does not change?
So just now I said that first of all, we should not consider wavelength as color. Okay. Color, yeah, wavelength changes. But yes, when light enters inside, its wavelength changes. When it comes out, its wavelength changes again. So if its wavelength changes by whatever 4 nanometer or whatever, uh, it will, when it comes out, it will have exactly same wavelength as it had before. So there will be no change in the wavelength as long as it is in one particular material. When it is in air, it doesn't matter it is coming from glass or it is coming from somewhere else. As long as it is in the air, it will have exactly same wavelength.
In actually, sir, I have seen through the prism some green light converted into red light. I have seen, sir.
No, that's different. You know that energy cannot change. Energy is always constant. So the energy doesn't change unless the energy is given to something or taken from somewhere. So unless there is a loss of energy or unless light receives energy from somewhere, which happens, for example, in Raman spectroscopy, and there are some other techniques also, where the energy of photon can change, but only if it receives or gives energy to some way, right? Otherwise, absolutely no, because energy is always constant.
It means color of light does not depend upon wavelength.
So that's what I was trying to explain, that wavelength can change. But again, the color of light is not really the wavelength. Color of light is what is going into your brain. Your brain perceives the color, right? So you don't know unless your brain tells you that this is red or green or blue. And how does brain tell you? Brain tells you from the electric signal, not from light. Light doesn't go to brain. So in any case, it is not related to light directly, but it is related to the energy of the light. And the energy of the light is related to the frequency, which is constant, but wavelength is not constant. So that's why it is better to associate it with wavelength. But ultimately, the feeling of color is coming from the electric signal, not from light.
Okay, sir. Thank you, sir. One more question, sir.
Yes.
Why light bends away or toward the normal during refraction? What is the real cause of attraction towards the normal or repel from the normal?
This is a question that requires a long time. I don't think I have that much of time to explain to you, but let me just put it in a very simple way that atoms have electric field and magnetic field because atoms have electrons moving inside atom, right? So
Yes, sir.
those electrons create electric field and they are moving around always, so their motion creates magnetic field. So each atom has electric and magnetic field all the time, right? Now
Yes,
when
sir.
light comes, then within that atom there are two kind of electric and magnetic fields, which of course they will combine with each other, because all electric field will create resultant electric field and all magnetic field will create resultant magnetic field at one particular point. So at every point, the value of electric and magnetic field changes, and that's why the direction of light changes, right? So now it depends
Yes, sir.
on the atom, what kind of atom it is. That means it depends on the refractive index, because refractive index basically depends on the material, and material means
Yes,
atoms. So that is
yes,
why
sir.
it changes, and it depends. In one kind of atom, it will change in one direction. In other kind of situation, it will change in the other direction.
Okay, sir. Thank you so much.
Excuse me, sir.
Good
Yeah.
evening, sir.
Excuse me,
I
sir.
have a
Yes.
question.
Excuse me, sir.
Yes. One
Yes,
person at a time, please.
yes, sir. Excuse me. Yes, sir. Very good morning. Sir,
Yeah, good
myself
morning.
is Usha Chakravarti. I teach physics 9 to 12 standard. So
Thank you.
my question
Yes.
is how to define in simple way, or how to explain in simple way of refractive index of class 10th students.
Sorry, I couldn't hear you clearly. Can you say it again? How to define what?
How to define refractive index of class 10th students in a simple way.
How to define? Of
Yes.
course, you can, if you want to use the formula, then there are, of course, formula depending upon the direction, right? So in terms of theta, you can define that. But ultimately, it all depends on the kind of material. That means it depends on what kind of atom you have. So structure of atom, that means number of electrons, number of protons, they decide what kind of electromagnetic field is created by the atoms inside the material. And so the material or the atoms inside material, they basically govern how light moves. But
Actually,
as long as definition is
many,
concerned, I think you can simply use the formula that defines.
many students ask many times what is the meaning of refractive index? What does it indicate? So I will not be able to make understand. So just I want to say what is refractive index for level of class 10 students?
So it's very difficult to answer in that way. But the reason, if you want to explain, is just saying that when you go from one material or one medium to another medium, the light has a difficulty to move, right? For example, if you are going in an empty space, walking in an empty space, and you are walking in a crowded space, your speed, your direction of motion may depend on that. So that is how two materials, the light within two materials, they move in a different direction. And because of that, the light bends. And so the refractive index is defined by how much it bends.
Okay, sir. Thank you.
Yeah.
Good evening, sir. First of all,
Good
thank you for
evening.
your wonderful talk. I
Yeah.
want to ask you that what is basic phenomena at atomic scale when light reflects from the surface of any material? Can we take as the same as any two uh, uh, any two uh, any two atom and a photon collision is it that, understand in that way, or an atom absorbing the photon and then emitting?
So there are many things that are involved here. Yes, one thing is scattering of light. And in scattering of light, it is possible that the atom absorbs the light and emits the light. But it is not really absorption and emission as two steps, but it is a kind of single step process. Okay, so if it is absorbed and then later on it is emitted, then it is not a scattering. Scattering is when the photon changes, maybe energy, or maybe doesn't change, but it remains the same. So for example, the names, I can tell you some of them: Rayleigh scattering and Raman scattering and Mie scattering and so on. So in those cases, yes, this is what happens, but this is not reflection, right? So reflection has to follow exact geometry. And if you talk about atomic level, this is, I don't know at which level you are, but it will be slightly difficult to explain because that involves quantum mechanics at that level. So we cannot use the normal physics at atomic scale that probably you already know, right? So how light interacts at atomic scale is very different. And you have to consider again that the wavelength is much, 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 much larger than atoms. So atom will not exactly see light as we explain light in the larger scale. But in terms of photons, yes, that means if we consider as a package of energy, then we have different way of considering this, and that involves all quantum mechanical treatment. But as long as you go with geometrical optics, you can simply say that, okay, the light is hitting just like a ball hits wall and then it goes away exactly at the same angle at which it reflects. So same way light also reflects exactly at the same angle at which it is incident.
Arnav,
Excuse me,
do
sir.
you have any question? Yes.
Excuse me, sir. Sir, I'm
Yes,
Arnav
please.
Saxena from class 10th. My question
Okay.
is that diffraction limit of is too large, and to break this limit and confine the light, it is done through a metallic nanoparticle. Sir, you told
Okay.
us that it is done through a metallic nanoparticle instead of insulator, so that electrons can freely move. Sir, sir, then why is this needed?
I didn't get your question. Why? What is needed?
Sir, my question is that why do we when we break the limit and confine of the light within the size of a few nanometers, this is done through a metallic nanoparticle. So, sir, why is it done through a metallic nanoparticle?
So why do we need metallic nanoparticle? Is that your question?
Yes, sir.
Okay, so what we have discussed here is that when you have light on a particle, and if you have free electrons, if you have free charge carriers, then those free charge carriers can move around, because whenever you shine light, the electrons will of course experience force because of that light, right? So whether it is insulator or metal or whatever. But in case of insulator, they cannot still move. They cannot move, leave one atom and go to the other atom. That means they cannot move from one place to other place. So that means if you don't have a metal, there will be no movement of free charge carrier. There will be no movement of charge carriers. So even if you shine light, nothing will happen. So when nothing happens, it's not interesting. We are not considering that. But when it is metal nanoparticle has a property, or metal has this property, that the particles, electrons or free charge carriers, they can move around from one atom to another, and they are always moving. In fact, what happens is that they apply force on each other, because, for example, you consider only electrons. So there are so many electrons which are free to move from one atom to another atom. They will apply force on each other without any light. And so they will push each other, right? So they will push each other as much as possible. So they can go away as much as possible. That means they can go onto the surface. And after surface, they cannot go further beyond. So they have to stay on the surface. But even on the surface, they continue to apply force on each other. So that means they cannot stop on the surface. They have to keep moving on the surface. So under the influence of their own forces, they always move and move and move on the surface. So they are the free charge carriers which are moving around. And because of their movement, they also create some kind of electric field, because they are electrons or they are positive charges. So they create electric field which is changing because they are moving. So even without shining any light, you can still have some kind of electromagnetic field on the surface, which I have not discussed. That happens even for the larger particle. But what we are interested today was about nanoparticles. So in nanoparticles, they preferably or forcefully oscillate with exactly same frequency as the light that we shine, because they are separated by the electric field of external light, and that external light oscillates. So they have to oscillate exactly at the same frequency. And so the electric and magnetic field created by them oscillates at the same frequency. And that's why we have oscillating electromagnetic field, which is confined near the surface of the particle, but it still has the same frequency as the propagating light. That's the reason why we have to use this kind of material where we can get free electrons or free charge carriers.
Thank you, sir.
Yeah.
Good evening, sir. I have a question.
Yes. Yes, go
Sir,
ahead.
I'm Diotima from class 9. I
Yes.
have a question. Sir, how did the scientists invent the evanescent light if it cannot be seen? And I mean, who discovered it? And sir,
Who discovered?
how, sir, the evanescent light, if it cannot be seen?
Yes, I don't know. I don't actually remember who saw it or who discovered it for the first time. Unfortunately, I should know that, but I don't know.
Okay, sir.
Well,
And sir,
but let me answer you. But we don't see evanescent light, of course, because evanescent light is not moving, right? So because it vanishes within few tenths of nanometer, so it doesn't go to our eyes, and we cannot see something, any light, if it doesn't go into our eyes. So evanescent light is a non-propagating light. We can never ever see that. But as I said, that when you shine a nanoparticle with certain frequency light, propagating light, then the energy is dumped from propagating light to the particle and to the evanescent light. But this cannot happen because particle cannot collect energy forever. So finally, once the evanescent light is stabilized, after that the energy goes out. So it has to scatter light, exactly same light which is there as evanescent light, exact same frequency, exact same energy. So that's why we don't see the evanescent light, but we see the scatter light, which has same property as the evanescent light, and that is why we understand what is evanescent light. How is the evanescent light? What are the properties of that light? So we don't see evanescent light, but we see a light which is identical to evanescent light, except that it is moving.
thank
Okay.
you, sir. And sir, why cannot we make images using non-propagating light?
Say it again, can you please?
Sir, why cannot we make images using using propagating light?
Yeah, because the propagating light, of course, we do always make image. If you take a picture from your camera, of course, you make image using propagating light. But that propagating light does not have all information about the object, because light is coming from the object, let's say, right? And then it goes into the lens. And at the lens, some part of that light is converted into evanescent light. And that evanescent light is not moving, so it doesn't participate in making the image. So that means at the image, you lose some information, right? Because the light that comes from the object has such information as size of the object and the shape of the object and everything. But that information is lost because that information is not going to the place where image is made. And that is why you can make the image with propagating light, and we always make image with propagating light, but that propagating light does not have a resolution of nanometer. So at nanometer scale, we lose some information. But if you are not worried about nanometer scale, if you are taking a picture of a person or a flower or something which is several centimeter to meter size, you don't have to worry anything, because at that scale, you don't lose anything.
Thank you, sir. I have another question, sir.
Go
So,
ahead.
can the radiated energy be more than the incoming energy, or is it always equal?
So once again, the question is related to the conservation of energy, right? So total energy
Yes,
should
sir.
remain always same. It can convert from one form to another form, but total energy should be the same. So if you consider the energy before the light comes and the energy after light goes away, should be the same, right? So that means total energy should not change. Whatever energy comes, exactly same energy should go away. Larger than that energy cannot go because it needs that extra energy from somewhere.
Yes, sir. Thank you so much, sir. I have another
Yeah.
question, sir. You
Go ahead.
told about cloaking devices for invisibility. So
Yes,
how are they made? I mean, I have
Mr. India.
always heard about them in fiction stories, always.
You want to become Mr. India? Yeah. Okay. So this is done by something called metamaterial. Okay. So the material, material is the normal material that we see in the nature. They are made of atoms. But metamaterials is something that you make exactly same as a material, but man-made material. So we call it metamaterial. Now you can devise it, you can make it in such a way, as I told you, that atom can control the direction of light because it has electric and magnetic field. But if you create a material and somehow create electromagnetic field inside that according to your choice, that means then you can control the direction of light, because once light enters, you add more electric and magnetic field to the electric and magnetic field coming from the light. So at any point within that material, the total electric and magnetic field can be under your control. So you can decide how much total electric and magnetic field you want at a certain point. So that means, in other words, one can control the direction of the light. Okay, so in normal case, we are talking about refraction, law of refraction, and at what angle it moves and so on. But in this case, you can control the direction of light even in the opposite direction. Or you can make a gradient of this material so that the light goes in certain path. So that means you can avoid light passing through some point, right? So light goes through certain path that you have decided, and light doesn't go from some area which you have also decided by designing this metamaterial. Now, if you sit in that part where light doesn't go, you will not be seen, because you can be seen only light falls on you and you scatter that light. So you will become invisible.
Oh, thank you so much, sir. Sir, can I ask two more last questions?
Go ahead.
Sir, whenever we see our eyes, they act as lens, so the image is inverted, and then the brain receives the electric signal. But sir, how does the brain, get the correct actual image, like from the electric signal? Like, can there be any error sometimes? I mean, whatever we see, is it really always the truth, or like,
Okay,
no?
how do you know what is correct image? Do you know what is correct image?
No, sir.
You don't know, right? How do you know what is upside and what is down or downwards? Do you know if image is upside down or downside up, what it is? How you don't know, because you always see that. Your brain is trained to see that, right? So as I was telling you about color also, that your brain is trained to recognize certain electric signal as green color, certain electric signal as red color, certain electric signal as blue color, right? Similarly, it is trained to recognize certain direction as upward, certain direction as downward. And so it is so much trained that you think, okay, this is what it is. But the other person may think a different way, because his brain, his eyes, his optical paths within the system, it can be different. So maybe you think this is perfect, but the same thing is maybe showing up differently for the different person, but he thinks that different direction or different way is the perfect way. So for both of them, it is perfect, but maybe showing up differently in two different minds, two different brains. So it is all about brain, all about how your brain is trained to recognize things.
Sir, how is the
That's why
brain
you know
really
that
trained?
small children who are just born, if you look at their eyes, you will see that they are trying to somehow understand what is what. They are trying to collect that data, and that data trains their brain, right?
Yes, sir.
So
Yes, sir.
you can
Thank
watch
you,
some
sir.
small children and you can recognize that.
Yes, sir. Sir, one more last question. So last.
Yes.
So, how is quantum computing? How is it related to photonics?
In quantum computing, instead of electric signals, they use optical signals, and they use photons. So that is why it is related.
Thank you so much, sir. For I had asked so many questions to you, but thank you so much.
That's not a problem. I'm happy that you asked.
Excuse me, sir.
Yep.
Sir, you were saying that there was. Excuse. You were saying when the particles are too close, lambda, which means the distance is lambda upon 2.
Yes.
The images overlap, which means that their information of that light information is getting deleted.
Why it is deleted? No, the thing is that they overlap, so you cannot recognize them as two independent particles, right? So in reality, you know that they are separated. They are two different particles. For example, you know for sure that they are separated by 10 nanometer. But when you make image, those images are 200 nanometer and 200 nanometer. So they, if the center of these two circles are separated by 10 nanometer, they will completely overlap. Okay, so it's just that they overlap and you cannot recognize them as two separate things. Okay, information is lost when you lose some kind of light. So yes, when you are making the image, in that process, of course, you are losing the information. That is why you don't have information about the size. That is why it is very large. But once
Sir, but
the image is made, then there is no loss of information in that process.
Sir, but then it is breaking the law of the quantum mechanics because it states that the information cannot be destroyed.
I don't know what you're saying. Yeah, I don't know about that. Information cannot be
Destroyed.
lost.
Yes, no.
Okay, I don't know. In what reference you are saying that? What is information? Okay, go ahead.
Sir, actually, I again had another question. Sir, can I do that?
Yeah.
Sir,
Yes.
one image you showed where there were different colors which were put inside silver. So, I thought that was the yellow color more brighter. Was it my error or something? Or it was looking as if the yellow color was more brighter than the green one. Is it
Could
like
be.
the
Could be.
scattering of light? Can it be different?
Could be. I have not talked about color, intensity of the color at all. That really depends on many things. Yeah, could be. Why not? There's nothing that stops. I have not talked about the intensity. So there are many reasons why intensity could be large and small.
Thank you, sir.
Can you see my video? Can you see me in the video? I can show you something. Just a second. If you can see my video, I will show you one cup here. Can you see this in my hand?
Yes, yes, sir.
Okay.
Yes, sir.
So this looks pink, right? But
Yes, sir.
this cup has gold inside and gold nanoparticles. And the gold nanoparticles are of the size so that it scatters the pink light. I don't know which wavelength, maybe multiple particles, multiple colors, but ultimately it looks like pinkish.
So what is this?
This is a glass, and there are gold nanoparticles in this glass. So you can see that the color comes from the size of the particle.
So Pranjal is raising his hand. So Pranjal, what is your question? Can you
Good
ask?
evening, sir. Good evening, sir.
Yeah, good evening. Go ahead, ask the question.
Yes, sir. Sir, basically, I had a doubt, sir, that suppose we have a sir vertical slab which has a gradient of refractive index along it, which is increasing from bottom to top.
Okay.
And suppose, sir, we say that a plane wavefront is incident on the slab. So, sir, by Huygens principle, we would expect the wavefront to be like bent upwards due to the induced time lag. But, sir, if I consider it from the point of view of ray optics, sir, by applying Snell's law locally at every point, sir, I would expect it to not deviate because, sir, because there is normal incident of rays. So, sir, why is there a conflict between when I look at it from the point of view of ray optics and wave optics?
If your light is going perpendicular to the material, yes, you say that it will bend. I didn't follow your question exactly.
Sir, basically, sir, I think, sir, if you are familiar with so basically slabs that have like variable refractive index.
That's
So,
okay. So you shine light perpendicular to
yes,
the
sir.
slab,
If there
right?
is a incident wavefront, which is a plane wavefront, so sir, it
Yes.
should bend according to Huygens principle, right? Because different
Why?
portions of refractive index will induce a time lag.
What? I'm sorry, I'm not able to visualize what you are saying. So wavefront is quite small. What is the, if you consider one stream of light or you consider multiple photons, what is it?
Sir, basically that is my doubt, sir. Do we consider, sir, why is there a conflict between like wave optics and ray optics at this point? Because, sir,
There is no conflict at all. So if it is incident, if it has plane wavefront, and if it is incident perpendicular, it will go without any deviation.
sir, but what if that slab has a variable refractive index, like at every point?
No, but it is in the direction of propagation, right?
Yes, sir.
That's what I'm not able to visualize. What is your question? So if the variation in refractive index is in the direction of propagation, there will be no change in the direction.
Sir, yeah, so that's what I'm sorry, sir, I didn't mean that, sir. It's not in the direction of propagation. It is perpendicular to the direction of propagation, the variation in refractive index.
Then it doesn't matter because it changes as light propagates, right? If there is a variation in some other direction, how does it matter?
Sir, basically, sir, I
Because
was considering it.
at every point of the wavefront, in the direction of propagation, there will be no change. So as light propagates, no part of wavefront will see any variation, right?
So, sir, basically, sir, if I have such a slab, then the light should come out as expected. Sir, it should not deviate and it should just come out perpendicular.
No, if I understand your question correctly, even if there is a variation of refractive index within a wavefront, at any point on the wavefront, there is no variation as light propagates, right? You said that in the direction of propagation, there is no variation.
Sir, that's not exactly my question, sir. What I'm trying to say, sir, suppose, sir, we have a vertical glass slab and the refractive index is increasing from bottom to top.
It doesn't matter direction. I don't care about direction. I'm worried about the propagation direction and the variation of
so the propagation direction of the light rays is perpendicular to the slab, so that would like appear as a plane wavefront incident on the.
Can you tell me what is the direction of variation of refractive index?
Sir, in the vertical direction, sir, bottom to top.
So that means in the direction of propagation.
So the direction of propagation, so the incident light ray would be horizontal, right?
Don't confuse. Just listen to my question and answer exactly to the point. Is light moving in vertical direction?
No, sir. It's incident horizontally.
Incident horizontally.
Yes, sir. Okay. On the slab.
Okay. In horizontal direction, there is no variation in refractive index.
No, sir. Not locally.
Not anywhere, right? It only changes vertically.
Yes, sir. Only vertical changes.
So then, what is the problem?
Sir, if I
as it moves in horizontal direction, you consider any point of the wavefront, there will be no change in refractive index as it propagates.
Yes,
Right?
sir, for individual component, because sir, if I take a single wavefront in that light ray and I consider the point at the top of the slab and at the bottom, sir, the refractive index are different
You
at
have
those
to
points.
you have to gather your own points carefully. So what I understand what you're saying, there will be no change. There is absolutely no problem about it, because in
Okay,
the
sir.
direction of propagation, there is no change for any point of the wavefront.
So one more question, sir. Is there, sir, a way to visualize, sir, why back waves are almost zero in Huygens principle?
Say it again.
Sir, is there any way to like theoretically say or visualize why the back wave amplitudes are almost zero in Huygens principle?
I really don't know.
Thank you, sir.
Yeah.
So we are not
Good
going to
evening.
take any. Hello.
Excuse me, sir. Can I ask you a question, please?
Yes, please.
Yes.
Sir, at the nanoscale, why does the light does not focus at a point?
Because the field changes, variation in the field, electric and magnetic field, is very large, right? Electromagnetic field changes at the scale of wavelength. So if you consider the volume of, if you consider the space from where light is going, so within that space, the electromagnetic field changes at very large scale compared to nano scale. So if you just, maybe you can recognize or remember my picture in one of the slides where I showed nanoparticle on which light was falling.
Yes,
So
sir.
within the nanoparticle, because it is so small, the variation of electric field as light passes through is negligible. Okay? And so it does not recognize light at all. So that means there will be actually no interaction of light and you cannot make the image correctly. Is
Yes,
that
sir. Sir,
your
I have
question?
another question.
Mm.
Sir, do we get complete information once we create the evanescent light? Like by using the metallic ions?
So I don't know the definition of complete, but yes, you get much better information. As I showed you some images at nanoscale that we can see carbon nanotube, for example, with 10 nanometer diameter. And I mean, the image diameter is 10 nanometer, actual diameter is only 2 nanometer. But if it was not about evanescent light, then the same image would appear with a size of 300 nanometer, for example. So if you have 2 nanometer carbon nanotube and you try to make the image size will be 300 nanometer in general case. So you can reduce from that 300 to 10 nanometer, but if you don't call it perfect, then of course you can improve it further and further. And I have not gone much into the detail, but now the technology has developed a bit better than what I have explained already. And people can go down to molecular scale also. So they can visualize molecular scale by visible light.
Yes, sir. Sir, I have another question. Can we recognize complete information if we use an insulator instead of an metal?
So again, I have just explained this some time ago
Yes,
that
sir, you have.
that in insulator you do not have free charge carriers, right?
Yes,
So
sir.
that means you have no oscillation, no free charge carriers are there. So even if you shine light on it, individual electrons will experience some force, but they are bound by stronger force with the atoms. So they are not going to leave the atom and they will still stay in the same atom. So that's why there will be no free charge carriers, there will be no oscillation of free charge carriers, there will be no evanescent light.
Okay, sir. And
Yeah.
sir, Prabhat cannot open his mic, so he is asking a question. Like, how is Einstein's energy mass equivalence and Planck's constant used in de Broglie's equation as energy mass equivalence of relativity and Planck's constant is quantum.
Okay, leave this question for next time, okay? This
Okay,
is
sir.
too long and too complicated.
And sir, I have another question actually.
Not really related to this talk.
Yes,
Yeah,
sir. So can I ask another question? One
go
last
ahead.
question.
Yes, yes.
So, like after we have created our own evanescent light, then we were
Hmm.
able to get the almost complete information, and the color was same, the frequency was same, so we got the color. So,
Hmm.
well, if the color was same as the propagation light,
Hmm.
as the propagating light, then did we also get the like exact information? Can we also have communication by using the optical waves?
Communication? What do you mean by communication?
So, like
Are you
small
talking about
bits
optic?
of information.
So communication usually means, of course, like fiber optics or something, but you need to have propagation of light for that, right? Communication is transferring information from one place
Yes,
to other
sir.
place. So if light doesn't move, how will you do that?
Yes, sir.
So yeah, you need propagating light for that. Anybody else?
So, I'm sorry, sir, but people are messaging me to ask you the questions.
Why
How
can't
did
they
we
ask
discover
directly?
the I don't know, sir. How did we discover the existence of evanescent light in the first place? I think you have already answered that.
Yes, I have. So
Okay, sir.
yes.
So as we come to the end of this presentation, and students, if you have any question, you can ask on the YouTube channel. Shiksha Sopan has its YouTube channel, and where you can find the video as well. Right. So today's illuminating journey through the world of light in our webinar, I would like to remind you that this is not the final call for the science students. We have many more such enlightening sessions lined up for you. On behalf of National and Vishika Network of India, NANI, Shiksha Sopan, and the Indian Association of Physics Teachers, IAPT, I extend our deepest gratitude to Dr. Prabhat Verma for his insightful and engaging presentation on nanoscale photonics. His expertise has illuminated a fascinating and potentially transformative field for all of us. To the aspiring scientists and inquisitive minds joining us today, we urge you to continue your exploration of the captivating realms of physics and optics. As exponential opportunity awaits you, the National Anveshika Experimental Skill Test NAEST 2024 offers a prestigious platform for students from grades 9 to 12 alongside bachelor's and master's program in science to showcase their exponential knowledge and skills in physics. We strongly encourage you to register for NAST 2024. This program promises to be a rewarding learning experience and a chance to distinguish yourself among your peers. Calling all science explorers, are you ready to dive deeper into the fascinating world of physics? The National Anveshika Experimental Skill Test 2024 registration is open, and the last date will be 20th May. And we are delighted to announce our next captivating webinar on May 18th, 2024 at 6 p.m. Indian Standard Time. We are honored to have Professor H.C. Verma, sir, a distinguished former professor at IIT Kanpur, as our esteemed guest speaker. Professor Verma will dwell into the intriguing interaction of computational science and Pingla Chand Sastra. This promises to be a highly interactive session. So please come prepared with pen and paper to take for note taking. Thank you once again for joining us today. We look forward to welcome you to our upcoming events and continuing this rewarding scientific journey together. Thank you. Thank you, sir.
Thank you so much.